Hello everyone, now that we've gone over Riemann sums, let's formally link that to the definite integral. Now let's go ahead and say f is a continuous function on the closed interval ab. So here's our function. Notice that it's continuous on this particular closed interval from a to b. Let's also go ahead and make sure that we talk about the partition of the particular closed interval ab, and let's go ahead and call that p. So notice that I've gone ahead and partitioned this into 5 regular intervals. Now, if the values of x star, let's go ahead and just review again what x star was. If we take a look at our Riemann sum, the x star is actually the value that we chose, the x value that we chose on each one of the partitions, to then go ahead and substitute into the function to come up with the height of our rectangle. So notice that what we're going to say then is that the values of x star is going to be something that's on each one of these interval widths. So it could be x of 0, it could be x of 1 for this particular interval here. And remember that when we went ahead and actually evaluated the upper Riemann sum or the lower Riemann sum, then we used either one of these endpoints here. Now when it comes to this particular definition though, it doesn't matter where the x star is going to be, so long as it's somewhere on that particular partition. And that's what this says. Okay? If the values x star are in each one of the partitions that we have, and it doesn't matter where it is because it can be arbitrarily chosen so long as that it's on the partition, then r, which is going to be equal to the summation from I is equal to 1 to n of x of I star times by delta x of I is going to be called the Riemann sum of f on the closed interval ab for the partition P and the selection of x of I star. So there's nothing different with regards to how we are interpreting the Riemann sum. The only difference at this particular point is that we can actually choose any particular value on the partition, on each one of the partitions that we want to use to indeed go ahead and calculate what that Riemann sum is. Now, if P is a regular partition, then of course delta x of I is going to be b minus a over n, as in this case over here, where n is actually going to be equal to 5 for all integer values of I. Now, if the limit as n approaches infinity, okay, in other words, the number of partitions that we have become infinite, and delta x also goes to 0. So in other words, we're increasing the number of partitions, and therefore what's happening then is each one of the partitions is actually going to be going to 0. The partition lengths are going to 0. And the limit as n approaches infinity of r is equal to the limit as n approaches infinity of what we've described as the Riemann sum. If those limits exist, then we say that f is integrable on the closed interval from a to b, and this is what we write. So we write the definite integral from a to b of f of x d of x is equal to the limit as n approaches infinity of the Riemann sum. So now let's go ahead and just take a look at some of the things, hopefully, that you can now make connections to. Notice that when we talked about this part here, we talked about this part over here being actually the height of the rectangle, and this part over here actually being the width of the partition. Now, notice that when we actually go ahead and take a look at this part here, the f of x here is going to be our function, and many of us were asking before, what is the purpose of d of x? Well, the interpretation of d of x, when we write it as a Riemann sum, is actually going to be the partition width. Okay, so nothing new here with regards to how to go about taking or evaluating an indefinite integral, but I'm thinking that this is probably the first time that we'll see the actual connection between the Riemann sums and the definite integral itself. Now, of course, there's going to be certain results that are going to be important, and this is one of the biggest ones here. It says if f is continuous on ab, the closed interval ab, it is integrable on the closed interval ab as well. And now, the reason for that is because the limit is going to exist. What we're going to see later is that if the limit does not exist, then we're going to have to approach these types of integrals in a different way. Now, of course, all the other properties that we know of definite integrals are still valid and should still be used, but now hopefully the connection between the Riemann sum as well as the definite integral is clear. So we'll take a look at some examples and we'll go ahead and answer any questions the next time that we meet in class. See you then. Bye-bye.